We're now going to take a look at something called Graham's Law. Now, Graham's Law talks about how the molecular weight of a gas is going to affect its speed. Let's say I have a bunch of different molecules. Let's say I have a molecule of helium, and I have a molecule of oxygen, and a molecule of UF6, which is a giant molecule. If they're all in the same container, they have the same average temperature. And if they have the same temperature, they're going to have the same kinetic energy. And though we don't explicitly discuss kinetic energy in this class, if you've learned about kinetic energy previously, you know that it depends on the mass of the molecule and its speed. So when I have a gas like helium that's lighter, if it has a lower mass, it's going to have a higher velocity. So whenever we have a lighter molecule, on average, it's going to be moving faster. And when I have a heavier molecule, for example, like UF6, it's going to be moving slower. We have some equations that describe this more explicitly. Our first equation that we're going to look at relates the rates. Rate 1 over rate 2 equals the molecular weight of gas 2 over the molecular weight of gas 1. This is for rate. So when I say rate, we're talking about how fast the gas is moving. Typically, it's going to be in meters per second or centimeters per second. Now, however, if I have something, I could also be talking about the distance that a gas travels. How far gas 1 travels relative to how far gas 2 travels. This should clearly be a 1, and it's not. That is also a diagonal relationship. Distance is going to be measured in units of meters or centimeters. We have a third relationship we sometimes use, and it's just simply going to depend on the type of problem that you're given. T1 over T2 equals the square root of molecular weight 1 over molecular weight 2. If you see the difference in these three formulas, you'll notice that for distance and rate, one molecule's molecular weight lines up diagonally opposite its rate. Same thing with its distance, but with time, it lines up straight across. So let's take a look at a sample problem. We're going to decide which formula to use, and then we're going to use it. So hydrogen gas moves at 400 centimeters per second. Find the speed of neon. Centimeters per second is a rate. So I'm going to use rate 1 over rate 2 equals molecular weight 2 over molecular weight 1. It doesn't matter which gas I decide is gas 1 and which gas I decide is gas 2. I prefer, however, to have my unknown in the numerator. So if I'm going to find the speed of neon, I'm going to put its unknown speed here. And the molecular weight of neon, which is 20, goes there. The speed of hydrogen is 400, and the molecular weight of hydrogen, don't forget hydrogen is H2, the molecular weight of 2 will go here. So now solving, 2 divided by 20, I'm going to square root that side of the equation. And now I have x over 400 equals 0.316. Cross multiplying, I get 126.5. And the other rate was in centimeters per second, so this one's also in centimeters per second. Now, I want to consider, does this answer make sense? Neon is a heavier gas than hydrogen, so I should expect to get a slower rate for it than I did for hydrogen. Indeed, I did. A good sign. Here's a second Graham's law example. An unknown gas escapes a container in 20 seconds, while neon escapes in 15 seconds. We're going to find the molecular weight of the unknown. Okay, first thing I want to do is I want to consider which formula I should be using. Is this distance, rate, or time? So to look at that, I'm going to look at the units here. And when I see that that's time, I now know of my formula choices that I'm going to use the one that sets up straight across, this formula here. So T1 over T2 equals the square root of molecular weight 1 over molecular weight 2. I'm going to have the unknown gas be gas 1. The unknown gas escapes in 20 seconds. I'm going to put its molecular weight straight across from it. So right across here, I put my X. Neon escapes in 15 seconds. Neon has a molecular weight of 20. Coincidence that there's two 20s in the same problem. Okay, so now I'm going to divide 20 by 15. 20 divided by 15 gives me 1.33 equals the square root of X over 20. To get rid of that square root, I'm going to square both sides. 1.33 squared, I have 1.78 now equals X over 20. Cross multiplying gives me a molecular weight of 35.6. The units of molecular weight, if you want to include them, are grams per mole.